Hello, welcome to part 3 of lecture 6. Now we're going to be talking about how to prove existence and non-existence statements. So let's go ahead and get started. Let's start with existence statements because they're typically a little bit easier. And let's look at this theorem. So this theorem says for every irrational number x, let's just ignore for a sec, the precise definition of what irrational means. There exists an irrational number y such that when you add them together, you get something that's rational and positive. So it's like if you're given some sort of like nasty number, like the devil hands you an irrational number, you can always find another one. There exists one. That's what makes this an existence statement. So that you add them together, they're rational and positive. So one really good way of making sense of these kinds of theorems and like building intuition for what's going on is to come up with examples. So what are some good, maybe irrational numbers with some x's? Well, a pretty classic one is maybe like square root 2. The square root of any prime will work, in fact. Maybe what could I add to square root of 2 to make it rational and positive? Well, maybe, if I just did, y equals negative square root 2, if I wanted to cancel it out, that's good because now it's going to be rational. I'd get x plus y is 0, but there's a problem that it needs to also be positive. So maybe I could just bump y up a bit, and then we'll get something positive. So what if I did, what I did 1, so like negative square root 2 like plus 1, right? And then when I do that, I get square root 2 plus 1 minus square root 2. Those two cancel. Yeah, and then I get 1. Okay, this is looking good. I think I could do the same thing if I picked a different irrational number. So like, for example, pi. Then it looks like if I did like y equals 1 minus pi, maybe 2 minus pi or 3 minus pi. Let's try something different. Let's try 3 minus pi just for kicks and giggles. Then if I do x plus y, well, I get pi plus 3 minus pi. And okay, again, yeah, by sort of design, the pi's cancel and we get 3. Okay, and both of these are rational and positive. Okay, so before we really dive into it, what does it mean for something to be irrational? Well, we say a real number is irrational if it's not rational. Okay, that's not terribly informative. What does it mean to be rational? We say a real number x is rational if it can be written as, so like x equals m over n for integers m and n, where in particular n is not equal to 0. We don't want to divide by 0. So something is rational if it's a fraction, like if you can write it as a fraction. So some examples of rational numbers are like 1/2 or 3/4 or 52 over 73. But rational numbers also include integers like 7 and 5 because you can write those as 7 over 1 and 5 over 1. So, and then we say something's irrational if it can't be written this way. And there's a lot of history, especially in like the Greek tradition, about irrational numbers, which is really interesting. But I won't bore you with it here. Let's kind of focus on this. So let's brainstorm. This statement is really asking us to, like, if we're given some sort of arbitrary x, so it's for every single x, so some arbitrary one, we need to like really like construct, explicitly show what y is equal to so that x plus y is rational and positive. So we kind of got a hint from our examples up here that maybe we could do something with this, like, this sort of irrational, 1 minus the irrational sort of number. So maybe for x, we could choose y equals 1 minus x, right? Just kind of like we did with the square root of 2. And then, x plus y, well, what do we get? We can substitute what we know y is equal to, so we get x plus 1 minus x. And then the x's cancel out, which is pretty cool, just kind of like in our example, and we get 1. And then that's rational and positive. So there's a little bit of an issue here because we have several things we need to show. So we defined our choice of y. That's good. We said y is equal to 1 minus x. But we also need to show that it's irrational. Okay. So, and how do you show something's irrational? Typically, the best way to show something's irrational is to do proof by contradiction, right? Y is irrational since if you were able to write it as like m over n, then, well, what does that say about x? Well, we know x is equal to, if we rearrange this equation up here, we know that x is equal to 1 minus y, but then x is equal to 1 minus m over n, and that's going to be, if we do your whole fraction combined and stuff, this is n minus m over n. Both of these, top and bottom, are integers. This would say x is rational, which is no good because by hypothesis, x is supposed to be irrational. Okay, so that's kind of what that would be. Then we would need to check that x plus y is rational. Well, 1 is certainly rational, so that'll always work. And then we need to make sure it's positive. Well, 1 is definitely positive, so that also works. So those two will be pretty fine. The real meat and potatoes is defining the choice of y and showing that that choice does work, that it is indeed an irrational number. Okay, so let's go ahead and write out the formal proof. So we're going to suppose, or assume, that x is irrational. Now, let's define or set y to be equal to 1 minus x. We claim that y is irrational. Right, we've defined our choice of y. That's good. We've done this piece. And now we want to go ahead and show that y is irrational. And we want to make sure it satisfies all these things. Okay. If y was not, or rather if you could say not irrational, if you could say if y was rational, then y equals m over n for integers m and n with n not equal to 0. But then there's an issue, right, with the scratch work we did above. But then we know that x is equal to 1 minus y, rearranging this equation up here. And then we know that that's 1 minus m over n, and then we know that's n minus m over n, where n minus m and n are both in z with n not equal to 0, which is impossible by hypothesis, since x is irrational. So y is rational. Okay, so we checked off those two boxes. Now we just have to do the last two. So now, x plus y. Now we want to make sure that this is rational and positive. Well, we can do some of the scratch work that we kind of did from up here. We can go ahead and put that in our proof. So we know that x plus y is x plus, if we substitute what we know y is, we get 1 minus x, and then the two x's cancel. That's good. That's 1. You can say this. This is looking really good. So we have x plus y equals 1. And then you can say which is indeed rational and positive. Done. We found a y, we checked it was irrational, then we showed that the sum of x plus y was indeed rational and positive. So I think we're pretty good. Now it's always good to go back through your proof and read it out loud and make sure it flows. And make sure that there's nothing that feels like it's jumping over or is unclear. So a really good thing to do is read the proof that I just wrote and go through it and see how you could improve it, because there's always room for improvement. So how would you improve this proof? It's a good exercise. Okay. In the meantime, let's talk about proving a non-existent statement. Non-existent statements are a little funny. So let's do it with this particular theorem. So the theorem is, let q be an odd integer. We want to prove that the equation x squared minus x minus q equals 0 has no integer solutions. Okay. This is a little strange. No integer solutions. What's the integer here? I'm confused. Let's just break it down. So what does this theorem even say? So it's like, okay, q here is fixed, right? So q is an odd integer. So maybe it's like 5 or 7. So like we're looking at like x squared minus x minus 5 equals 0. Or maybe x squared minus x minus 13 equals 0. And we're saying that this has no integer solutions, which means that there's no integer x so that these equations hold. Right? So we know from like calculus and pre-calculus that these quadratics, they always have, most 2 real solutions. And what this is saying is that those solutions, if they exist, they're never going to be integers. Right? There does not exist an integer that you could plug in for x so that this is true. Right? There's no integer I could plug in for x squared minus x minus 13 so that I get 0 out. Okay. So what are some of the definitions involved? Let's kind of brainstorm. So this is strange. So we're really saying that q is an odd integer. So we know that q is going to be equal to maybe 2k plus 1 for k in z. Okay. Now, non-existent statements are weird. Like, how would you even prove this directly? Like, q is not integer. I guess you could plug this into the equation, maybe like x squared minus x and then minus 2k plus 1 equals 0. But I don't know, that doesn't really tell me anything. It doesn't seem clear what the issue is here. So maybe contrapositive or contradiction might be good. I'll tell you right now, if you're trying to prove non-existent statements, the classic choice is contradiction, right? So you, contradiction. You want to assume that the thing does exist. So assume there is some integer, a, so a is an integer, so that it does satisfy this equation, right? It is a solution, so that like a squared minus a minus q is equal to 0. And then we're going to find some problem. So again, not obvious what the problem is, but we know what q looks like. Okay, so let's plug it in. So we'd have like a squared minus a minus 2k plus 1 equals 0. Strange. What if let's move the 2k over. So let's move it in the sketch. So let's write this as a squared minus a equals 2k plus 1. And now this is where, you're still like, okay, what is this supposed to get me? But notably, we have an odd number on one side. And a classic kind of contradiction to do is to say an even is equal to an odd. That's a really good contradiction to get to. We have an odd on one side, so if we can show that a squared minus a is always even, we have our contradiction. Okay, and that this is for any integer, right? Why would that be true? Why is this always even? Well, you could try some cases. If you do like 2 for a, you get like 2 squared minus 2. That would be 4 minus 2. That's 2. Well, that's even. Okay. What if you did 3? Well, then you get 9 minus 3, which is 6. That's also even. Okay. Interesting. So it looks like it works out. And it looks like, maybe it might be nice to do this depending on whether A is odd or even. So this little result right here, we would want to prove by cases. When A is odd and when A is even. So it looks like this proof really hinges on this little fact that A squared minus A is always even. Now, whenever you have a proof that really hinges on one key fact, it's classic to write a lemma. So a lemma is a little result before your theorem that helps you prove the bigger result. So let's go ahead and before we write the formal proof, let's go ahead and write down a lemma. So lemma, we say for any integer A squared minus A is always even. There's different ways you could write this lemma. You could also say if A is an integer, then A squared minus A is even, things like that. Let's go ahead and prove. So proof. Well, okay, what are we actually going to do? Well, we're going to do it by cases. And what are these cases going to look like? Well, if A is odd, then it's 2k plus 1. And then A squared minus A is going to be equal to 2k plus 1 squared minus 2k plus 1. And then what's that going to be? It's going to be 4k squared plus 4k plus 1 minus 2k plus 1. Okay, let's combine some things. So we get 4k squared plus 2k plus 2. Oh, this looks good. This looks really good because now we got a 2 in each of these terms. I can pull it out. I get 2, and let me write it down here. 2 times 2k squared plus k plus 1. This is good. I got 2 times the integer. This shows it's even. I think something similar would happen if A is even. Then we get A is equal to 2k. So that says that A squared minus A is going to be 2k squared minus 2k. So that's 4k squared minus 2k. Again, I can pull a 2 out from both terms, so I get 2 times 2k squared minus k. Again, that looks pretty even to me. Okay, let's use this sketch in our lemma. So proof, let A be an integer. We're going to do 2 cases, so you could say we proceed by cases to tell the reader that we're going to do 2 different ones. Case 1, A is odd. So then we know that A is equal to 2k plus 1 for k in the integers. So then we just kind of repeat the work that we did above. We know that A squared minus A is going to be 2k plus 1 squared plus, minus 2k plus 1. I might have made a mistake with the parentheses up here. Yeah, I did. Whoopsies. You can make sure you distribute your minus signs, otherwise you make the same mistake I did. There we go. That looks a little bit better. Okay. All right. Sorry about that. Okay. So we get 2k squared, 2k plus 1 squared minus 2k plus 1. And then we get 4k squared plus 4k plus 1 minus 2k minus 1, distributing the minus sign. These ones cancel, so we get 4k squared plus 4k. Then subtracting away the 2k, we get plus 2k. And then we get 2 times 2k squared plus k. So where 2k squared plus k is an integer, so a squared minus a is even. And the second case is similar, though not identical, so we are not allowed to use without loss of generality here. You say A is even, then A is equal to 2k, for again, k in the integers. So a squared minus a. We replace it, we get 2k squared minus 2k. And then we get 4k squared minus 2k. And again, pulling out that 2 gives us what we want. So now we need to say that this thing inside here is an integer, where 2k squared minus k is an integer. So a squared minus a is even. The result holds in both cases. So that concludes our lemma. Whew, all right. A little bit of legwork to do at the beginning there, but now I think it's going to make our main result that we want to show, this like weird non-existence theorem, I think it's going to make it a lot easier to prove. So let's go back up and look at what we're doing. So we wanted to do this by contradiction, and we wanted to assume that there was some integer. Okay, yeah, and then we want to show that we get an even equals an odd, and that'll be our contradiction. Let's go ahead and write out this proof now. So suppose q is an odd integer. We will proceed by contradiction. So in a proof by contradiction, we're allowed to assume our hypothesis and not the conclusion, right? So we get to assume there is some integer a, so that it satisfies that equation, right? It's a solution. So that a squared minus a minus q equals 0. Okay, now what our sketch look like? It looks like we want to go ahead and move the q over and replace it with its definition. Maybe this is a little out of order, but that's okay. We could say then a squared minus a equals q. Okay? By our lemma, a squared minus a is even. However, by hypothesis, q is odd. So we have an even integer equals an odd integer, which is impossible. And I think that concludes our proof. We found something that's impossible. That's a proof by contradiction. Very nice. Excellent. So a good exercise to do is actually convince yourself, write a proof, like why is it impossible that an even integer can't, why can't an even integer equal an odd integer? I think you would do something similar. Assume that there is one that equals, write down the definitions, substitute into the equality that you've assumed, and see if you can get some contradiction. That'd be a really good exercise. I recommend giving it a try. Now make sure to come into class and discussion on Monday with questions about the lectures.